The next topic that will be introduced is this topic of Hess's Law. And Hess's Law is important because it allows us to take a reaction, as most reactions are, which is carried out in a series of steps, not just one individual step, and take each of those individual delta H values for the steps and add them together and say that that's going to be the delta H of our overall reaction. So the sum of the individual enthalpy changes for each step. So what we see here in this reaction shown below is that my delta H1, which is the total enthalpy change, is going to be equal to the sum of the individual steps, which we believe to be the actual mechanism of this reaction, which we're going to say are delta H2 and delta H3. So the overall delta H1, the overall enthalpy change is going to be equal to the sum of the two enthalpy changes for these steps here. So we can estimate delta H values using published enthalpy change values for that are known for many reactions. So this is convenient because we know that delta H is a state function and our total enthalpy change depends only on the initial state of the reactants and then the final state of the products. So using this information, let's see if we can take a look at sample exercise 7 here and find a way that we could manipulate these two equations to find the enthalpy change for this overall reaction here. So if that's my overall reaction, somehow I have to add together these two equations in a way that I would end up with this overall reaction. So let's see here. For equation 1, I have A plus B yields C, and that's 5 kilojoules in the forward direction. So I definitely need to double that. So I'm going to say 2A plus 2B will yield 2C, and that will give me a delta H equal to 10 kilojoules. And I know that I need twice as much because in my overall reaction, I have 2A here. So then with the next reaction, I need 2B to cancel out on the other side. I need C here to add to the C on the product side. So I'm going to flip this reaction. And what happens when I do that is I'm going to have D will yield 2B plus C. So my overall reaction here, we'll get in 1 second, but we want to note that the delta H now goes from being -10 to +10 since I flipped this reaction. So the first equation I manipulated by multiplying by 2. So I multiplied my delta H by 2, but this one I'm flipping, so it's like I'm multiplying by -1. So now my overall reaction looks like 2A plus D. The 2B will cancel out because it's on both the reactant and product side. And I have 3C. As I want it to match my overall reaction now, I can add together those individual enthalpy changes and see that for this reaction, the overall delta H is 20 kilojoules. So we can do something similar using real equations here, and we can calculate the delta H for this overall reaction. So this is the overall reaction, and we're given these individual steps down here and their enthalpy changes. So in this first reaction, I noticed that my product is on the reactant side. So I'm going to make a note that I need to flip this equation, mainly because of that product being on the wrong side. And that's all I want to do right now for that equation. Let's look at this second one here. So carbon is in the final overall equation, but there's 2 of them. So I'm going to multiply everything in this equation by 2. I'll just make a note over here. And then this last equation, H2 looks good. It's on the right side, so I'm going to just leave it alone for now. So I'm just going to put a check here and say that I'm going to leave my equation 3, we'll call it, alone. So let's make these changes. So if I flip the first equation, I'm going to have 2CO2 plus H2O will yield C2H2 plus 5 halves O2. And then for my second equation here, I'm going to have 2 carbon plus O2 will yield CO2. Oh, so we need to double these, right? So everything was multiplied by 2. And now in my last equation, I'm just going to leave that alone. So I just have H2 plus, oh, we'll squeeze it over here, 1/2 O2 yields H2O. So let's see what happens here if I kind of make the sum here, take the sum of all these values. So what do I have? I have 2O2 and then 1/2. So if we were to combine these terms here, if we were to take that as halves, that would be 4 divided by 2 to give me 2. And then we add to that 1 more half. So this is actually the same value as we see on the product side of 5 halves. So our oxygens will cancel out. And then we're left with water as well on each side. So we have removed all of our intermediates and catalysts, and let's also remove this CO2. So we've removed a lot, so that's a good sign that if everything cancels out and we're left with what we're looking for, we've made the right changes to our enthalpy value. So I see 2C plus H2 over here, and that matches up with my overall equation. And on the product side, I see just one product, C2H2. So everything looks good because my overall reaction checks out here. So now I'm going to make these changes. So I'm going to change this from negative 1299.6 to positive 1299.6. Then I'm going to take this negative 393.5. I'm going to multiply that by 2. And then this last value here, I'm going to leave that negative 285.8. And these are all kilojoules. So we can find the product of 2 times negative 393.5, add that to positive 1299.6, and then subtract 285.8. So overall, we would see a positive 226 kilojoules for this reaction.